right. Hello, everyone. Thank you for joining us today here at Zillow. We're always happy to host people and meetups. It really gives us a great opportunity to talk with you guys and network. My name is Hoelscher. I'm a machine learning engineer here at Zillow. And I've been working here on the data science and engineering team for about 2.5 years now. And so I've actually had the great opportunity to work with the team building and re-architecting the current Zestimate pipeline. And the new pipeline that I'm going to share with you guys today has been largely inspired by Lambda Architecture. What I hope you take away from this talk is a better understanding of what Lambda Architecture is, if you're not familiar, and also seeing a real-world example of how to implement that in this case, the Zestimate. So without further ado, let's actually start with the Zestimate itself and its goals. So for those who aren't familiar, the Zestimate is our estimated market value for individual homes nationwide. So we strive, as you see in the screenshot, to put a home value on every rooftop in the nation. So every day, the Zestimate team thinks about how we can actually improve this estimate. And from a data science perspective, improvement is based on some of these goals I've highlighted right here. So and I'm going to actually talk about a few of them here, but not cover all of them. So let's start with the easy one. We want the Zestimate to be very, very accurate. And so what that means for us is that when a home actually sells on the market and transacts, we would like the Zestimate to be as close to that sale price as possible. Another important goal for us is stability over time. So when we produce estimates every day, we would like there to be no erratic behavior day to day. Another important goal is actually responding to user updates. So users actually right now can go to their home and update facts about their property, and we will return a news estimate in real time. And this is very important because we want users to interact with their Zestimate and improve it and actually see their home facts improving the algorithm. So in a sense, these are the goals that our pipeline needs to support, and these are the goals that we're thinking about when we're designing our new pipeline. So I was actually, we did architecture overview for the Zestimate in 2015, and this actually happened at another meetup group, and this was when I first joined Zillow, and a few of my colleagues actually presented this. So I was flipping through the slide deck there and realized just how out of date the architecture was. So in these 2.5 years, we've actually evolved dramatically. And so what exactly has changed? So then versus now here. So at the core, the Zestimate in 2015 was largely written in R. And so our team was actually comprised of a lot of R language experts. And we even built an in-house R framework for doing parallelization. It's similar to MapReduce. So we were a small team back then, mostly data scientists actually, very few to zero engineers. Most of our data scientists wore both hats at the time. And so we actually leaned on a lot of different groups within Zillow. So we work closely with database administrators to actually update the Zestimates on the live site, and they provided us enormous help. But 2 years later now, in 2017, we've made a huge hiring push across all skill sets and invited engineers to join the fray. So Python has actually become the language of choice now in our team, thanks actually in part to its long history of support within the Apache Spark framework, which we currently use for our new Zestimate algorithm. So we started actually leveraging more and more cloud-based solutions and services, such as Amazon Simple Storage Service for data store in the cloud, Elastic MapReduce for cluster computing. And so no longer were we actually bottlenecked by an individual host. We actually had a lot of on-prem hosts that data scientists would fight for each day. And now someone can actually go spin up their own cluster or their own EC2 instance. So it makes prototyping much, much more enjoyable. So with all these changes, we had the opportunity to start afresh and design a new system that would handle large amounts of data in the cloud and that would reliably scale horizontally, and most importantly, would meet the goals of this estimate. So in terms of the Lambda architecture, this idea was actually introduced by Nathan Mars, and you might be familiar with him if you've ever used Apache Storm, as he's the creator of that. And I actually highly recommend his book here if you are not really familiar with Lambda architecture, but really want to go deep into the subject. So it really paints the foundations of Lambda architecture and gives you great case studies for actually implementing that. So what is Lambda architecture? It is a generic data processing architecture that is horizontally scalable. It's fault tolerant, both in terms of human errors as well as hardware failures, and it's also capable of low latency responses. So shortly, we'll actually see what this architecture looks like, but I wanted to actually talk about this trade-off that I present at the bottom here. So low latency generally means that you're producing low accuracy results as well, but especially when you're dealing with enormous amounts of data. And then you can also choose a high latency system, but you're choosing higher accuracy. And so let's actually explore this concept more because it really underpins Lambda architecture. So I'm taking this example actually from Databricks. So they've done a blog post back in 2016 when they first actually introduced their approximation functions in Apache Spark. And so in this case, we're looking at this function called a Proxy Quantile. And so this algorithm is requiring a user to specify a target error bound, and then the result is guaranteed to be within this error bound. So this algorithm pretty much can be adjusted to trade accuracy against computational time and memory. So in the example that we're looking at right here, we're looking at Amazon review data set and trying to just simply calculate quantiles for the length of these documents. And so on the x-axis at the bottom, we have plotted the target residual increasing from left to right. And so you can see that the computational time, as we expect, drops dramatically as we accept a higher error bound. And then the right-hand side, you see various quantiles actually computed. When you're looking at the median here, the red at the bottom, it's actually relatively stable and highly accurate, even at a higher target residual. But when you are dealing with more extreme quantiles, you're starting to make trade-offs in terms of the accuracy. So returning back to the high-level Lambda architecture with this idea, we can start by simply building a batch system. So this is, I kind of want you to ignore this whole diagram right now and just look at the left side. So we have data, and we want to process that data and answer a question. So we can simply do that with a batch layer because it's pretty much low complexity. And so when we run a query and try to get some insight from our data, we'll actually be freezing our master data set. And so during that time where we actually compute results on that master data set, new data has been coming in that we actually haven't seen before. So this is really the gap that Lambda architecture is trying to solve, is that you have actually produced a result for your user that's answered the query, but at the same time, it actually does not capture every piece of data. So it's not timely anymore. So in this case, we introduced something called a speed layer. And this is looking at all new data and trying to produce a low latency view to answer your query. And so at this point with that speed layer, you're starting to consider algorithms that are approximating based on your data set. And your batch layer can actually rely on higher latency algorithms, but be more accurate. So now you have two views, a batch view as well as a real-time view. And you now just need to reconcile those two views in order to return a result that is both highly accurate and low latency to your user. So at this point, I kind of wanted to dive into the Zestimate itself. So we're going to be talking about each of these individual layers and how they apply to the Zestimate. So we're going to start with this master data architecture. So this is actually rather simple, and that's the nice thing about a service like Amazon S3. So we have on the left these generic data generating processes. These are some of the types of services that we actually see dumping data into our data lake here. In this case, you can have an Amazon Kinesis service dumping data to the S3 bucket, and we've denoted this as a raw bucket because we only expect raw data to be there. And so the key thing here is that you really want to lock down your permissions to prevent data deletes and updates. And this means that you're not relying on updates anymore. And so your data is essentially immutable and always going to be appending new data. And we want our master data to never be touched never be mutated within this bucket. And that's why we lock down permissions here at Zillow. So let's dive into one of these statements that I've made, which is data is immutable. And this is really important for Lambda architecture. So I wanted to walk through this example. Sorry about the obnoxious screen. That's pretty bright. So we're going to actually walk through this example of a home. So we're seeing the evolution of this home over time. So it's been constructed in 2010 as 2 bedrooms and 1 bath. 5 years later, a full bath was added. As a result, it increased the square foot. There's actually a transaction that happened after that. And then a new owner comes in and says, this home is not large enough for me, so I'm going to add another bedroom as well as another half bath. So in a typical relational database, what you do is actually overwrite all these records so that you'd only have 1 record in the end, not all 3 of these records. So the view we'd be left with is a 1 record view with 3 beds, 2.5 baths, 1,800 square feet. But we've actually lost a lot of information, and as a result, we can't really tell this whole story of how this house has changed over time. So why is this important for data science? Let's walk through another example here. So data is eternally true. And what I mean by this is that as soon as you attach a timestamp to a piece of data, you are saying that this data was true at this point. And if there were 2 bathrooms for this home in 2015, that means that this fact will always exist. That might not be true for the present, but in 2015, this house did in fact have 2 bathrooms. And so that's what we talk about when we say data is eternally true. So in our relational database view, we will have actually collapsed that top table into 1 row because we're updating this record. And now we have this transaction that I mentioned before. So this property ID sold for $450,000 in 2015. And so this is the exchange from the old owner to the new owner. But from a data science perspective, if we just have that top table collapsed into 1 row, then we're actually assigning that bathroom count to this transaction, that bathroom count from the future to this transaction in the past. And this could have negative consequences for our training data set. And, obviously this is quite a trivial example, but you can imagine a larger set of attributes that are being kind of confused over time because we're not allowing data to be immutable and eternally true. And so at this point, I wanted to talk about the batch layer. Excuse me. So after we migrated our data to S3, we began work on the batch layer. And this is how we approach this problem chronologically too. We started with the data, making sure that's in the cloud, and then started work on the batch layer. Remember, we were actually hiring a lot of people, so we started with a very small team and took each of these tasks at a single task at a time. So we have our raw data in S3. And so we actually use Apache Spark for our Zestimate process. And of course, Spark has a data frame reader that can read directly from S3. One of the problems that you could deal with this append model is actually appending very small files. And this is pretty much the curse of small files in Hadoop. And it afflicts Apache Spark as well. So really what we'd ideally like to see is our reads being incredibly fast because we're reading very few large blocks of data instead of a lot of small files. So to deal with this problem, we actually have a vacuuming process. And this could be as simple as like a disk copy or S3 disk copy job that's actually relying on copying the S3 data to an EMR cluster, which will be housing your HDFS. So at that point, the data is on HDFS, it's aggregated, so reads are much more optimized. So now we enter the three phases of the Zestimate. So it's simply ETL, train, and score for us. And the ETL is really responsible for producing training sets and scoring sets. And the training, of course, is training a variety of models. And the scoring is then scoring the 100 million properties that we have nationwide. And so what we do here is we have a separate bucket for our transformed data. So again, the raw is our master set that we never want to touch. So our models, our training sets, our scoring sets, our validation metrics, this is all time-stamped with a particular Zestimate run and saved in this transformed bucket that represents derivative data so that we can trace back in case we have problems in production. So let's dive a little bit into these few layers. So I want to highlight the functions here. So this ETL layer, again, is responsible for interfacing with that master data set. And we really want to arrive at a cleaner and standardized view of the data so that we can consume that by our models. And we have a wide variety of data sources that we actually deal with. So we need to pull appropriate features from each and build a very rich feature set. Something that we invest very, very heavily in is actually cleaning our data. Of course, everyone's familiar with garbage in, garbage out, and it really, really afflicts us here at Zillow with dirty data. You know, one example that we joke about, but it's actually a reality of our day-to-day work, is these fat finger errors. So someone entering 500 square feet into instead of 5,000 square feet can have really negative effects on how we perceive that home's value. So we really invest in this cleaning process and take a longitudinal view of our data to understand what are expected and normal values. So you can imagine that this actually becomes quite expensive because we end up cleaning the data by looking at the entire history of the data, as well as actually partitioning this data so that it can be used by training and scoring. And we do use Parquet at this point, and most of our raw data sources are actually in JSON, although we do mandate schema contracts between the producer and consumer so that we can conform to the right data type. So now we're dealing with this Parquet format, which Spark loves, and we're entering our training and scoring phases. So training actually requires a large amount of memory, so we're using Spark as it was meant to be used. We're caching all of our training sets in memory and allowing multiple models to run across that same superset of training data, which is cached. We train models on various geographies, and so you can imagine that you're making a trade-off between dealing with highly skewed data versus a large enough volume of data for a training set. And then finally, our scoring is actually then repartitioned so that we can process uniform chunks of data very quickly. But the one thing is, after all this happens, all the data that we started with, that was frozen in time, and we actually got new data. So we've produced this view for the batch layer, but lots of home facts have come in, transactions have come in. So how do we start thinking about this? So the number one source of Zestimate error is actually the facts that flow into it. Bedrooms, bathrooms, square footage, all these, as I mentioned, can negatively impact how we perceive your home. So what we want to do is actually combat these data issues. And so what we open up a pathway for our users to actually interact with their home and update the facts, and they can see immediate change there. Beyond that, what we want to do is actually recalculate estimates when homes are listed. So you can imagine a home's been off the market for 20 years. The person that owns that home is not really interested in interacting with Zillow.com and updating their facts. But as soon as that home goes on the market, the facts are updated. You want your home to be represented accurately when you're trying to sell it. And so this is another important problem that we want to solve. So now we're starting to enter the speed layer architecture. So in this case, what we do is we've had that data that's stored in the S3 bucket, the transformed bucket. So that's our scoring sets, training sets, and models. And so we actually move most of those property facts that are required for scoring to a Redis cache that's made available for quick lookups of property facts. And so in this case, the speed layer, what it's doing, it's reading the same data as the batch layer. That's the expectation in Lambda architecture. So we have a Kinesis consumer here, and you can actually make some, there's a lot of different ways you could implement the consumer. So one of the big complaints about Lambda architecture is you're actually duplicating code. Here at Zillow, actually, we have two different teams, one working on the batch layer and one working on the speed layer. So you can imagine that your cross-team collaborations is actually very infrequent, and you could, as a result, have duplicate code being written in two different places. So some people actually like to have a Kinesis consumer using Spark streaming. So the nice thing about that is you can actually share these data frame API code across your batch layer and your speed layer. In our case, we were actually more interested in just using the Kinesis consumer library that Amazon provides, which actually Spark streaming is built on top of. And so it's actually more simple from our perspective. We weren't really sharing a lot of code, Spark code. We're actually sharing Python eggs across these packages. So we had these modularized functions that did cleaning for us, and that's what we'd be sharing instead of Spark. So from that perspective, we settled on the KCL. And you're also making this hardware trade-off. So with Spark, you'd expect this EMR cluster with at least 2 nodes, and you could actually rely on something like the EC2 instance in Amazon, which is just one host, and you can size that appropriately. So there's a cost savings there from our perspective. So obviously with the speed layer, we want to have it to be very, very low latency. And so it cannot rely on that longitudinal view of the data as I described earlier in our cleaning jobs. And so we pretty much forego a lot of those cleaning duties in the speed layer and allow our batch layer to do that. And I'll talk about how this isn't a problem in a few slides. So the other component here is actually our Zestimate API. And the Zestimate API was actually originally designed so that you could update your home facts. So you see at the bottom there, we have a request to update home facts, and the Zestimate API is going to handle that request. So every day after we finish our batch run, we'll actually update the Zestimate API with all of the models that were trained from the batch layer. So in our case, we're not relying necessarily on these incremental training algorithms, instead rely on batch layer training and reusing those so that we can be very, very nimble. In addition, we're using that same Redis cache to look up necessary property information that request might not send us. And I'd say one other interesting thing about our Zestimate API layer is that we rely on sharding of these pre-trained region models. And so we actually can't contain all of our models on one single host because they're too large. And as a result, we need to actually shard the models and then send requests that way. And so it's pretty much a bin packing problem where you're pretty much packing in based on the size of the models as well as the distribution of your requests. So this is the point I wanted to mention. So we've made these trade-offs in our speed layer about how we can't necessarily clean all of the data because a lot of these cleaning jobs are very long running. Again, the speed layer is not to be perfect. We talked about this earlier, how the speed layer can make mistakes, and we've accounted for that. It's meant to be lightning fast and respond to requests instantaneously. So the nice thing is that your batch layer is going to correct those mistakes eventually. So as a result, we can actually think of the speed layer view as ephemeral. It's not going to exist once our batch layer comes in and pretty much wipes most of that data. So the toy example I have here actually is lot size. So this is another tricky feature that we deal with. we generally expect people that send us data to send it in square feet, lot size in square feet. Sometimes they'll send it to us, they'll breach that schema contract and send it to us in acres. So this is what happens when you actually send us lot size when we're expecting square feet, but it's actually in acres. So now we're undervaluing how much land your property has. So you could actually imagine a GIS model that's trying to validate this lot size. So we're looking at a given property's parcel, we're approximating the area of that parcel, maybe we're starting to look at the neighbors around it and approximating those too, to get a signal on whether these lot sizes are clean or not. So the question then is, what happens if this model is very, very slow to compute? Well, your speed layer cannot afford to compute things very slowly. So maybe your decision is actually to throw that model away. But the good news is here, even though you've made these errant calculations, your batch layer will come in and save you. So lastly, I do want to talk about the serving layer. We actually, as a team, a data science and engineering team, haven't made too many investments into this. We're largely relying on a lot of the legacy system that we had 2 years ago. So this is really the DBA world that we're dealing with. So the key thing here is that we're dealing with two different SQL Server tables, one that the batch layer is writing to and one that the Zestimate API is going to be writing to. And so for us, it's actually really simple to reconcile data. This reconciliation can be more complex based on the algorithms that you're using within the Lambda architecture. For us, it's actually if a home fact comes in after we timestamp when the batch layer froze the data, then we can still serve that speed layers calculation. Otherwise, we're going to serve the batch layer. Pogo here is pretty much an in-house in-memory cache that lives on top of SQL Server, and so it handles a lot of our requests very, very quickly. So this is ultimately how you would view a home. So to bring all these pieces into a big picture view, one, we talked about how data should be immutable and human fault tolerant. And we can achieve that with S3 and storing just our data and always appending and not allowing anyone to delete or update. We allow our batch layer to actually do the heavy lifting, cleaning, and training. And then the speed layer can actually tackle some of these problems. And you can generally get away with just the batch layer if you don't have a business need for a speed layer. And I think that's the really nice thing about Lambda architecture here is that we've essentially evolved from 1, 2, 3 and added each component as we progressed on this project. So if you only need a batch layer and that satisfies your need, then you can do that. But later on, if you have this new need for a low latency response, then the speed layer is something that you should really investigate. And finally, that serving layer is going to reconcile those views to ensure the better estimation is chosen. So that's all I have. I'm going to introduce Andy here, and then we're going to do a joint Q&A afterward. Thank you. And so Andy's the research manager on the Zestimate, and he's going to talk about fixing Zestimates. Right.
Hey, folks. Thanks for coming out tonight. And pardon me in advance if I have a little cough here because I'm getting over a cold. So this exciting new Lambda architecture and moving our whole modeling system for the Zestimate to the cloud. It's been a big, long endeavor, but it's actually had some really exciting benefits along with, honestly, some increased complexity with this architecture. So, for example, once you're on the cloud, it's very easy to separate your computing and your storage, which enables us to dedicate much more computing resources to our modeling. And I'm here to argue that the upshot for everyone in this room is that if you're thinking of buying a home or you already own a home, we're going to make your Zestimate better because we've been able to make this transition. Now, before we get there, I do need to take a slight detour into a little bit about how we think about accuracy in real estate. And here at Zillow, so I'm going to throw a little bit of math at you. the two, so from a data science perspective, you often, when you're thinking about accuracy in models, things like root mean squared error, maybe if you're getting exotic mean absolute difference or something, these are sort of more classic sort of model evaluation metrics. But real estate's kind of an interesting space because you generally want to be working with relative error metrics instead of absolute error metrics. And the reason this is actually kind of very intuitive. There's a lot of heteroscedasticity, which is fancy stats words for as a home, $1 million home is going to have, all things being equal, more variance in its selling price or in its sale price than a $100,000 home. And to sort of intuitively get a grasp on why that might be, for those of you who have ever actually negotiated gone into a competitive bid, if you're going to be competing on a $1 million home, you're probably not sizing your bid increments at like $100 and $250 increments. You're probably doing it at thousands, maybe even $5,000 or $10,000 increments. Whereas if you're going to be buying a $100,000 house, yeah, hundreds of dollars, maybe $1,000. That's a big deal, both to the buyer and the seller. So this all really wraps up to needing to use relative error metrics like the percent error. And on top of this, we like to use the median absolute percent error as our preferred metric of central tendency to throw in a little bit more robustness. And because we actually think that is, for folks out here in the audience, it's actually probably one of the more intuitive metrics we can give folks to get a feel for how accurate is the Zestimate for your home or in this area, because 50% of the Zestimates are going to be closer to the sale price than whatever the MAPE is. 50% are going to be worse. Now, that's actually where we get to the second set of metrics, the percent within metrics. Those are very naturally, they sort of give you a sense of, if we set a goalpost at 5%, so how many homes sell within 5% of their estimate, that sort of is what your PE metric will go, or your percent within metric will be. So here the industry really seems to be in love with percent within 10% as a sort of their historical metric for measuring sort of the spread of the error instead of, standard deviations or variance. I think the reason that they get really into 10% is because human assessors have errors roughly of that order, about 8 to 10%. So I think that's how they like to measure themselves. I'm really more interested in 5% because I think we should just be as close as possible. And actually, within 20% has a special meaning here at Zillow because we like to say anything outside of that is crazy. One of our goals is to have no crazy estimates. And we're actually really forward with these metrics. This page here about the link up, this is actually one of the woefully least visited pages at Zillow, despite the fact that it's our accuracy scorecard. We update it quarterly. And actually, I know there's a lot of text and I don't think you should read it, but I want to point out that in Q1 of 2017, our median absolute percent error nationally was less than 6%. I think that's pretty exciting. And you can see, if you want to get into more detail, we have it for metro areas, and we're pretty honest about where we do good and where there's room for improvement. Texas is, by the way, a special state because sale prices are not public data there. So that makes estimating particularly challenging. So come take a look at this, but I've sort of gotten off topic of, did we actually make anyone's estimate in the room here better? Because probably most of us live in King County. So let me talk about benchmarking the two different architectures, because that's actually a non-trivial task. It's helpful. It turns out picking on King County is great because since it's where Zillow is, it's also where we dog food a lot of our own stuff. So we launched the Zestimate on the new architecture here in in late December. So from January onward this year, all Zestimates here have been produced on the new Lambda architecture. And then sort of how do we actually get at this accuracy? We actually construct things we call sale pairs. So because homes transact in relatively low volume, which is to say at any given month, I think if you look at like a King County, you'll see maybe 1,000 home transactions, maybe less than that sometimes in the winter. So that's not, you really need to be able to go back and average over some time periods, which necessitates this benchmarking system where you're able to go back in time, retrain models with data in the state of the system as if you were in the past. So for example, here, if we say there was a home that sold last year in April in Kent, we would like to be able to get a Zestimate from the month end, because that's where we like to pick the month ends when we're doing back testing, and for calculating the historical Zestimate charts on the home details page for those people who like to look at that stuff. I think the charts are fun. So we'll pick them at the month ends and try to get the state of the system. So what were recently sold homes as of March 2016 in King County, or July of 2010 in King County, what was listed then, what was listed in March, and be able to train models as if that was the state of the system. And as Stephen was saying, one of the great things about this Lambda architecture and moving to the cloud has just been we're able to take snapshots really frequently. So in the older relational database system, we also had these snapshots. They were much more expensive to construct and maintain, whereas here it was actually, we designed the system to be able to not only produce estimates in real time and going forward about what home values would be, but to make them real, but to be able to be conscious when building the architecture in leveraging some of the things like easy storage, easy and very expandable storage, to be able to store a lot of information to be able to recover past system states. Which is all a really roundabout way of saying that when we're going to compare the two architectures, we train models at the month ends. We match them to the most recent sale after that month end, although really you look at it from the other way around. So you see the sale and then you go back to the first month end. And so once we have these same, we have a set of sales in King County. We have estimates that are paired from the same date. We can actually sit down and say, okay, what have we got with this new architecture? And the good news is we've been able to leverage the architecture to reduce error substantially when we look across the set of the sales that are measured, same sales, but measured with estimates that are coming out of both systems. So not only did we improve our measure of central tendency, so MAPE has dropped, but we also brought the tail of the error distribution in, and less crazy estimates. And I'm actually personally think it's really cool that we actually broke 50% within 5%. So it means 1 out of every 2 homes here in King County and in Seattle sells within 5% of its estimate. I think that's an amazing achievement for a machine learning model. Although I still think there's even more to get. I think we can push this further. And something so I gave you the link to the accuracy page. Something that we don't do a lot publicly, but I think would be really interesting is to actually look at how our error works versus sale price. So here I've broken up the sales in King County into a lot of different buckets by about 100,000. Although once we get onto the homes that sell over $1 million, you have to make the buckets bigger, or else they get a little small. But you can see that basically our errors are a function of our sale data, and you tend to get a U-shaped distribution because most homes in King County sell between $300,000 and $800,000. At least that's what their prices were last year. By the time we get to the end of this year, who freaking knows? And so also thing you can see is that it's the new architecture and the models we're able to build on it by leveraging the bigger modularity and the computing resources improves our estimate accuracy across all price points. And actually we have particularly large gains at the high end, or so homes sort of over $800,000. And then just because again, I think people, I'm kind of interested to see how people like this. Here's just sort of breaking out just by home type. So SFR stands for single family residence, which in King County works out to detached homes as well as townhomes. So what's our accuracy for those homes in the new system and condos, which again, both the sort of more sprawling condo complexes you might see on the east side, and then the shiny new condo towers here in downtown will be in that category. A sharp-eyed person here has probably noticed that in general, the air tails on condos are not as large. So it's easy, the within metrics tend to be higher just because condos get built in sets. There's almost always a condo that's almost exactly like whatever condo is currently for sale, but one level up or around the corner. And one question I have for folks is this interesting data to see? Like we could put breakouts like this on the website. By a show of hands, who here would be interested in that? All right, that's really exciting. So yeah, I hope I've convinced you that not only that this architecture has definitely led to everyone in this room having a better grasp on what their home is worth. I also sort of have one more thing, because I know there's lots of data scientists in the room, and only so much time and so many folks that Zillow can hire to come and work on this. We've kind of been working on a solution for that. So I can't give you details, but I can tell you that tomorrow we are about to announce something, a partnership with Kaggle on a machine learning competition that is going to, we hope, is going to be as successful as the Netflix prize. If you want more details, you can follow that link, or when you wake up tomorrow morning, just do a little searching around for news about Zillow, news about Kaggle. I think it's going to be really exciting. It's going to be a big competition, and if you're in the room and you aren't already working for Zillow, you're eligible. I hope that many of you will be joining us and doing exciting and interesting work and getting to play with some of the excellent data we have here, and occasionally dirty data. But it's a good problem if you're a data scientist. So I'm going to have Stephen come back up, and we'll do a joint Q&A.
So in that case, it's shift. It's unfortunate. So, can I speak in the mic? Sorry. Yeah. So sorry. The question was, is our speed layer compensating for these fat fingers that we described, especially with attributes? And the answer I'll give you is that we're basically tackling certain sets of attributes. The attributes that are more likely to actually cause problems are those that we actually tackle in the speed layer. But there are some cases where we just can't afford computationally to solve those problems, though we are always looking for improving our algorithms to make them more incremental. But yes, this is a serious problem, and we really need to put a huge wall up in order to protect ourselves from this dirty data. Sorry. Yeah, let's take a look. So in this case, I guess I should have described this a little bit more. So it's in the Kinesis consumer down here. So it's going to be reading in new streaming data, and it's actually going to be importing some of our cleaning libraries from our batch layer. So we ship those as modules, Python modules. And so we can import the functions that we see as low cost but highly effective and run those within that Kinesis. So we're basically filtering that data, preparing it for a request, and then sending it off to the Zestimate API. Sorry, go ahead.
Yeah, so given the relatively low volume, 86,000 plus homes a month are being sold out, if the numbers look good as far as accuracy, what Zillow do to not overtrain models? I'm always interested in hearing people's solutions to this.
Yeah. So I think the biggest thing that'll get you in trouble when you're overfitting a model is having leakage, right, from information that would, for example, like if you could somehow get future sale prices into the model estimates as they're being generated, you would have a big overfitting problem. The other side of that is, and I probably didn't do, and the other answer to that question is really careful benchmarking. So I probably didn't. I know I spent a little bit of time talking about that, and I just don't want to get into huge detail there because it's a big subject. But creating model validation systems, which is the other half of what my team is responsible for, not just coming up with new things, but being very careful about the methodology for validating models, so that we create validation sets that mimic the problem as we have it here in the real time, which is, don't look at transactions that have already happened. Always make sure you're looking at transactions in the future, and just in general, being very, very careful about the state of the data you're building your models with when you're evaluating whether or not they'd help you out, so that you aren't having leakages come through the benchmarking data and fool you into thinking that you've made an improvement that's actually just an artifact of your evaluation system.
So in terms of like the feet versus acres example, how would you go about getting accurate training data to be able to detect things for similar things as knowledge?
Yeah. Yeah, I'll see if I can. Again, there's the secret sauce is the secret sauce, so I can't say too much. But I think with the acreage, though, I think it's actually a really intuitive thing to think about. So imagine that somebody has a half-acre lot, and they give us that in acres, so we don't even see like an integer if it's greater than 1. And your living area is some value obviously greater than a single square foot. Like, so there are some cases are really easy because they're just completely counterintuitive. And so you can just be like, okay, that literally is physically impossible to have a house with half a square foot of lot size. And essentially things that like all outlier detection or all sort of errant data detection are just sort of elaborations of what I described. They just cut finer and finer lines between what makes sense and what doesn't make sense.
So I think that's really, we can still handle that case, and maybe I'll highlight the slide that I want to refer to here. So in this case, we're actually looking at the historical data. So that's the nice thing about the batch layer, is that if there is a problem that we actually cause, then we can recompute our entire batch layer. Of course, you want to look into incremental optimizations if they're available, but that's the key point here, is that the raw data is always available for us. We're not making any mutations to that, but we are creating snapshots every day with our cleaning jobs that allow us to improve our algorithms over time, and especially handle cases that in the past as well. Right, and then we'll actually dump that snapshot to this transformed bucket. Let's get a question from the back. That's definitely one problem that my team, the engineering team that I belong to, has had to invest a lot of time into. We actually just made the migration from 1.6 to Spark 2 in the last month or two. And we had seen enormous improvements when we relied on the data frame API. So we actually had a sprint here where we basically said, find everything that's using RDD map and replace that with data frame API. So it's a serious problem in PySpark, and we're trying to basically minimize as many RDD API calls as we can at this point. I'd say another future consideration, if we do continue seeing performance bottlenecks, is trying to create different portions of our code, one that's in PySpark and one that's in Scala. The key reason why we chose PySpark is that we want to interface with data scientists. We don't want to scare them off, right? We want to share the code base. We want to have this dual ownership model, and PySpark allows us to do that.
You mentioned that there was maybe less data in the winter months for selling. What extent is your data seasonal? And if it is seasonal, how do you deal with that? Like maybe a certain threshold or prices change in various seasons or something like that. Like what extent is that an issue?
Yeah, let me see if I can. I think I can answer the first part of that question. I'm reasonably certain the second part is a deep, dark secret. So the first part is there's absolutely a strong seasonality in real estate data. And it's actually, one of the things that's really interesting is you can look at a place like Los Angeles or like Miami. You don't see nearly as strong seasonality because the weather is sunny and pleasant throughout most of the year, and home is photographed well then, and generally people are just like the market just has a lot less ebb and flow in listings. A place like Seattle, listings ebb, the amount of homes for sale and the amount of buyers out looking ebbs and flows quite a bit with the seasonality, because apparently it's no fun to go look for homes when it's windy and rainy and freezing cold. And so we definitely do take precautions to try to deal with that and try to ensure that our models don't have bias that has seasonal components in it, because that would be a big problem for the data.
Yep. Sure. Oops. I think Andy can walk along this line.
Yeah, I think honestly, the truth is that if you really want to get a sense for what models work, yeah, sign up on that competition teaser page and go try it yourself. Go tomorrow, go and try it yourself. I think you will come to some conclusions rather quickly about what works and what doesn't work. And that's honestly it's because real estate data is public. The algorithms really are our moat, our competitive moat, and we really can't talk in particularly strong detail about the models.
In the back.
Yeah, in the last quarter it was anyway, a little under 6. Right. So actually, that's a good point. I didn't make that point about the set of homes we measure accuracy on, but it's worth bringing up, which is we're looking to estimate the sale prices on homes that are fully valued arm's length market transactions. So, for example, homes that are passing from parents to children or through the foreclosure process are transactions that we are actively trying to not be modeling the prices of. We did a meetup recently where we talked a little bit about our efforts around images, and certainly home condition is something that you would hope you could infer from images of a home. There are places in the country where the tax assessors are kind enough to drive around and tell us that home looks shabby, and that's a great variable. I think that, again, that's about all I can say about that. But yes, of course, home condition matters a great deal in estimating homes, and is certainly a large source of the variation you see in sale price for homes that have, sort of similar spec sheet facts, so beds, baths, lot size, square footage.
Very back.
Let me see if I can. Yeah. So Zillow's actually part of how we've been making a name for ourselves. We have a whole team of crack PhD economists that actually addresses these sort of issues about housing policy and the state of the housing market. And there's actually a Zillow research blog where you can read their reports. And I believe that absolutely some of the work we do here in the Zestimate team gets employed by them to answer those sorts of questions.
Yep. Yep.
I didn't see it broken down in your numbers of how smooth you get
Interesting. Have we studied that? I'm sure we have.
We actually, I don't think we've really taken a look at it too closely, but one reason we haven't is that, as Stephen mentioned, the speed layer is very ephemeral. So though that estimate is likely has a shelf life of 12 to 24 hours or less. So it's very unlikely that it's actually going to be the last estimate you see before a home sells. Or even it's even very unlikely that that'll be the estimate that most potential buyers will see for the home, since listings are often coming up in the middle of the night. And so the speed layer's estimate won't be in place for very long before the batch layer gets to it.
Yep.
Yeah, so I guess the answer is we do have, our models are unbiased. We can't help it if the market ends up moving towards this estimate. I guess it just makes our estimates look more accurate. So far, every time we've joked about, whether or not we could add 1% to some random market's estimates to see if we could move the market, everyone shoots that down as obviously unethical behavior.
Have you tried doing this kind of validation in the market where you're not currently publishing?
The problem with that is that there's no such thing as a market we aren't publishing as estimate in, at least in the United States. We put estimates up on approximately 110 million homes, which is basically, as best we can tell, most residences in the United States. Two-word answer to that, which is secret sauce.
Any more questions? Oh, yes. Yeah. So I would say our daily snapshots that we're producing are approximately 1 terabyte in terms of the data that we use for Zestimates, and that's compressed Parquet. And then, sorry, your second question? Yes. Yes, that actually involves more work, like this cross-team collaboration with our database administrators. We really don't maintain the serving layer, so that's we need to work on that in the future. But we're actively moving a lot of our SQL Server databases to the cloud right now, simply for disaster recovery, and we really, really want people to start using the data lake even more. Yeah, our master data set definitely going to be there forever. Most of our transformed data sets, we'll have them move to infrequent access. Given that we're new to S3 relatively, I think we're still working on those policies and starting to see cases where we actually need this data. Yeah, I can imagine right now we're trying to just dump all the data, and we're actually cross-company trying to get more product teams to give us data. Really, we want the data lake to be the home of the data science and analytics team, and so we pretty much want more data than actually getting rid of data, but we are deeply thinking about IA and Glacier. Any other? All right, thank you, everyone. So we have some recruiters here as well. You guys can talk to us. Be happy to talk to you about these various positions we have open right now. Thank you so much for coming. Yeah, I'm too late. Yeah, how are you doing? Pretty good, yeah. Doing well.